before watching this video, you should have looked at example 3 in section 14.1 about the number of subsets, and hopefully you looked at the blue box, which tells you the formula for calculating the number of subsets, and that's just 2 to the n. What we want to understand is, why does that work? So let me switch to my shared screen and let's talk about that. Okay, so let's first of all be very clear what this is not. Okay, so when we're talking about number of subsets, the key thing is we must have a set. This requires a set. And the key is of known elements. All right, so this can't be talking about an event that hasn't yet happened. All right, so let's look at a set that's a reasonable size set. We could look at an entire deck of cards, but that would be a little bit complicated to start with. So let us start with a set of all queens in a deck of cards. Okay, so if I had that, I would have the queen of spades, the queen of clubs, switch to red, just to look nice. I'd have the queen of hearts and the queen of diamonds. Okay, those are the red ones. Okay, and what we need to determine is how many different possible groupings I could have. So a subset is any group of the above. All right, and so a subset could be, it could be the null set, anywhere from 0 to all 4 of the following, from the set, I'll say. So a really good way to look at this is think of this as counting. Let's let 0 equal not present in a subset, and 1 is equal to present. All right, we're kind of using logic here. So 0 means false, 1 means true. So this is actually a very good way to do this math. So let's go from the smallest subset to the largest. So I'll start with the smallest subset. That would be where we have none of them. So we have all zeros. All right, as we go towards the largest, those will all become ones. But now with zeros and ones, hopefully you're beginning to think about this as binary. In order to get all the possibilities, let's simply count in binary. All right, and so then we would have that's 1 in binary, 2 in binary would look like that. We can keep on going in binary. So remember, when we're in binary, this is the 2 to the 0 power column. This is the 2 to the first power, 2 to the second power, and 2 to the third power. Fortunately, those aren't big numbers. 2 to the third power is only 8. So to get to the third, well, this is the fourth row since 0 was the first row. This will be the number 3. So it's 2 to the first plus 2 to the 0. And hopefully you know that 2 to the 0 is the same as the ones place with zeros. And so by counting, I'll make sure that I don't miss any. So now I need the number 4, the 0 in front, the number 5, the number 6 in binary, the number 7 in binary, the number 8 in binary. Now we can keep on going. 9, 10, 11. Let me make sure. So 8, 12. We're almost there. 13, 14, and 15. That would be where all of them are there. Okay. So notice this is the number. If we were to do this in base 10, this is equal to 15 in base 10. And we had started all the way back here. 0 in binary is also 0 in base 10. So if I count from 0 to 15, that means there were 16 possibilities. To say 16 possible, so I can fit the word on the screen. Now, how many columns did we have? We had 4 columns. Well, 16 is equal to 2 to the 4th power, right? So our set had 4 things in it. Each one could either be present or not present in forming all of the possible subsets. We did an exhaustive list by counting in binary. So if there are 4 things, each of which could be there or not there, then there will be 2 to the 4th possible subsets that we could get out of it. Okay, so notice some of these subsets have 1 thing, some of them have 2. So if I look at the number of things in each subset, so the smallest has 0 things in it. This had 1, 1, 2. That's back to 1 element in the subset. This had 2 elements in the subset, 2. Now we're starting to see the 3s, although this goes back to just having 1, 2, 2, 3, back to 2, 3, and 3 again. And then this has all 4 things. There's only one way to get all 4. So we could have ordered this differently by starting with 0 things and then figuring out all the ways that we could have had 1 thing and then all of the ways that we have 2 things. But given the formula that the book gives, that the number of elements is just 2 to the n, or I'm sorry, number of possible subsets equals 2 to the n, it just lent itself very nicely to using binary. So it's an extremely easy formula to use. Let's consider an entire deck of cards, all right? So if we had 52 cards, the number of subsets would be extraordinarily high. Okay, so that would end up being 2 to the 52nd power. And so let me quickly pause this while I calculate that. And the number is extraordinary. Okay, in scientific notation, I'm not going to go to the ones place. It's 4.5 times 10 to the 15 subsets. Not quite as big as Avogadro's number, but that's an extraordinarily large number of subsets, which is why cards are so interesting. There are so many ways I could pick sets of cards out. Now, usually when we're playing card games, this is going to be more advanced. This is where we're going in the future. In the next few days, it's harder to calculate how many subsets with, say, 5 cards. So in a lot of games, you have maybe 5 cards in your hand at a time. You might have 7 cards in your hand, but that's a harder thing to calculate. It's easier. It's a very simple calculation to figure out how many total possible subsets. Now remember, these range from none to all 52 cards. So there aren't many games where you have 52 cards in your hands all at once. So this wouldn't really correspond to the number of possible hands that you could have in, say, a game of poker. But it is, you can see the numbers are extraordinarily high for the way that we could reorganize a deck. So that's all you need to do calculations for numbers of subsets. Simply take 2 to the n, where n is the number of elements in the set.